like figure out is it max or min, right? So optimization. Um, so you have to figure out, am I maximizing or minimizing? So max or min, and um, so we just figured out that since it says least expensive, we're trying to minimize. Second is you have to like come up with your constraint equation and the equation you're trying to maximize or minimize. So the constraint and then the formula or the equation to be maximized or minimized, to be max or min. Got it. So the constraint you set up really well. I liked that. It's x squared h, right, equals 125 because, well, it's a square base box. And so and we're trying to minimize. We figured that out. So like now you need the thing you're trying to maximize or minimize. So what would the formula be for that? Yeah, exactly. So we just figured out that what we need to minimize is the surface area. And what would the formula be for that? For surface area. Exactly. Excellent. X squared plus. You're so good at the fundament. Everything is. I've said this before many times, but everything you're supposed to know, you know. That's why it's so easy to work with you. Okay. All right. Great. Now, um, how did you come up with this formula, real quick? Well, sorry. Fair enough. Fair enough. But maybe a better question is like, how? Why is it not 5xh or whatever? Well, never mind. Never mind. I think I'm not asking good questions, so I'll stop because it says it's an open tank, so obviously you don't have to consider the top. Now, this formula, like we would proceed forward with just what we have right now, if there weren't prices built into the sides. But there are prices built into the sides. So somehow we have to like incorporate those in the in the equation that is to be maximized and minimized. So what are those things that are that we need to build in? So the $8 and the $4. Go ahead. It's okay. Well, it's okay. Sorry. Go ahead. It's okay. It's okay. So the x squared, that's the one that would cost $8. So you just multiply that by 8 because how whatever x squared is, whatever area that is, like it's gonna cost $8 per yard squared. And then the others, it's $4. So build that in that way. So now with surface area with cost, I guess like we can call it a cost function. So and it's a cost of the cost function is both a function of x and h, but yeah, it's c and for right now, right? So the c function, the cost function is 8x squared plus 16xh. And so, but again, like whatever it is that you're trying to maximize or minimize, there's like in multivariable calculus, you can keep two variables, but you're in single variable calculus, and therefore we have to somehow get rid of one of the variables from the cost function. And that is where the constraint function comes in. The constraint is going to help us eliminate one of the two variables in the cost function. So, which of the two variables should we eliminate, and how should we do that? Yep, exactly. That's what you should do. That's the path of least resistance, um, and so over x squared because this is clean. Obviously, if you try to solve for x, you have some square roots involved. So among other things, that's one reason why you don't want to solve for for x in the constraint function and substitute in the cost function. So now the cost is strictly of x, so we can call it c of x. So it's 8x squared, and then it's plus 16x, and then h is 125 over x squared. So 125 over x squared. So the cost function c of x is equal to it's equal to 8x squared plus, and then whatever 16 times 125 is. Hold on, I'll do it on the phone. Or if you beat me to it, go ahead. 16 times 125 is 2,000. Okay, that wasn't so hard. So plus 2,000. Well, 1x and 1x there take care of each other. So over x. But I'm going to prefer to write that as 2,000 x to the negative 1. Because ultimately we're going to take a derivative. And so I'd rather have it this way. And so where to next? Yeah. So because we're done with the function that we need to maximize or minimize, and we're done turning it into a single variable. We've used the constraint function. We've built in the cost. So yeah, we're ready. So c prime of x equals, talk to me.
16x.
Yep.
Negative 2,000x.
Yeah, negative 2,000 x to the negative 2, which is like negative 2,000 over x squared. And since we're going to set this equal to 0, right? Like, cause that's how we maximize and minimize. We, like, we don't want negative exponents. That's why I chose to stick it in the denominator. So now we need c prime of x to equal 0. So c prime of x is equal to 0 means 16x is equal to 2,000 over x squared. And pretty straightforward. Well, obviously I set it equal to 0 and then I added this over to the right side. But yeah, it's simple algebra that you get. So we can divide by 16. I think that'll return us to 125, right? And then divide by 16 on the right side. Obviously, it's gone there. So this is going to turn into 125. And like actually the dollar signs are also going to cancel, right? Because we're dividing by dollar sign, if we just do our unit analysis correct. Because we're trying to like find the dimensions right now, right? Okay, anyway, we multiply by x. So right now where we're at is x is equal to 125 over x squared. And then we multiply both sides by x squared, we get x cubed is equal to 125, from which we get x is equal to 5. Okay, not really surprising that it ended up having to be like a cube, because what happens is when you're trying to minimize surface area, it will end up being a cube frequently. So, and the dimension x made it a cube. That makes it almost seem trivial, but it's not. It's not so trivial. Now for h is going to be 125 over 5 squared. So h is going to be 125 over 25. Which is h is 5. Well, no, h is 25. So so these are the dimensions, and so but let's answer the question. What does it say? Find the dimensions of the least expensive tank. Well, we just did. So that's that. If it said actually find the least expensive tank, obviously, like, you could either take this h and x and plug it into this equation that we had here, or you can plug them into the one with x right there, and either is fine. Okay. Next is problem 6. So read it out loud for both of us.
Find the dimensions of the right circular cylinder of greatest volume that can be inscribed in a sphere of radius 6 inches.
Okay, so wait, sorry. You have a right circular cylinder, and that's like just a fancy word for saying a cylinder that's straight up, right? Like standing up instead of leaning. Okay. So we have our right circular cylinder. That's pretty good. That's pretty good for a morning drawing. And we need to put what in it? So it says inscribe a sphere. Find the dimension of a right circular cylinder of greatest volume that can be inscribed in a sphere of radius 6. I see. I drew the Not that it's a huge problem, but I drew this first when I should have drawn the sphere first and then put the cylinder in it, right? Okay, got it. So let's pay attention to what it is that we have to maximize or minimize. And it's pretty clear that, well, you tell me, what does it look like we have to maximize or minimize?
The cylinder
Yeah, the cylinder is what?
volume.
Yeah, so to be max and min, to be max or minimized is, first of all, it's max, right? It says greatest volume, yeah. And it is the cylinder's volume. So V equals, well, what would the volume of the cylinder be? Huh? Pi r squared. Yeah, the area of the base times the height. Exactly. That's just usually how volume is. Okay, all right. Pi r squared h. Got it. So obviously there are two variables. That's a problem, and we therefore need a constraint function. What, if anything, is useful towards to the end of the constraint function? What other information are we given to help us with the constraint function?
The sphere's radius is 6 inches.
Yeah, so that's the most crucial piece to this is like maybe that, like, well, obviously, like, you have to know everything else, but and this is kind of like SAT, but like notice that, like, and you're past that, but notice that, like, the most important line to draw is that line because it brings a connection between the sphere and the cylinder, right? Like, and if the cylinder is properly inscribed in the sphere, they should be touching at this spot right there, right? And the sphere also is a three-dimensional shape, so you know it has like a radius of sorts like this, right? Well, it has like a what's called a great circle inside it, which is this here, right? And I just drew it, but I'll draw it over. Okay, hold on. Okay. So what I have to do is now I should draw this line right here. Well, actually, we need to connect them, right? We need to connect the radius of the sphere and the cylinder. So the radius of the sphere is 6. I don't like, as a Christian, I know you're a Christian too, I don't like the number 6 repeating, so I'll use like 7. Like, so, anyway, let's say that that's 7. And, well, like, I'll just help on this one, right? Like, but you'll be able to replicate it on a similar problem. So what I just tried to highlight in black right there, what is the height of that up to here? Or how can I represent that? H over, yes, exactly. And it's because I'm trying to form a triangle. And this right here is, I'm going to call it little r, and it's the same r as what we wrote right here. It's the radius of the cylinder. I intentionally didn't write big R for the sphere because we know its value, right? Like, so we want it not complicated. We want as few variables as possible. So, like for the sphere, which clearly has a larger radius than the cylinder's radius top and bottom, for the sphere, we're just going to say 7, and then I've got my R, my H over 2, and so then here we are. Like, that's, the sphere is not involved in any significant way. Like, we don't need to bring the sphere's volume, blah, blah, equation, blah, blah, blah. Like, this is all the connection that we need. Like, if the cylinder is on the sphere, they have to be touching here. If that's the case, we can form this little right triangle, which will give us helpful relations between the variables we need related. So the constraint function is going to be r squared plus h over 2 squared is equal to 49. You understand where that came from, right? Yeah. Okay. And this time, the path of least resistance would be to solve for r squared. You should see why, because then it's clean. It's cleaner. Like, because r squared is 49 minus h squared over 4. It's really not that much better than solving for h squared. But, you know, like, h squared would have a denominator in it, blah, blah, blah. That's why r squared is just like from where we're at on the constraint function. It's very easy to get to this, so choose the path of least resistance. Now the volume that we're trying to maximize or minimize is strictly a function of one variable, and it's v of r, so that's going to say pi, well actually, sorry, it's going to have to be v of h, because we're substituting for r squared. So it's v of h, and it's going to be pi times, in place of r squared, we would put 49 minus h squared over 4, and then that is multiplied by h. So v of h is going to equal, well, if we distribute the pi and the h from the pi from the left, the h from the right, we should write 49 pi h, and then minus pi over 4 h cubed, right? And what's the next thing I should do? There you go, because now we're all ready. So v prime of h is going to equal, well, you talk this time. Go ahead.
49 pi
Yep.
minus pi over 4 3h squared.
Yeah, 3 pi over 4 h squared. And we set this equal to 0, meaning that 49 pi will have to equal 3 pi over 4 h squared. Next, we multiply by 4 over 3 pi. So 49 pi times 4 over 3 pi is going to equal h squared. And so this and this are like canceled, and you have 49 times 4. What's that? Like, it's like 50 times 4 minus 4, right? So that's 200 minus 4, so that's 196, which is nice. Well, kind of. 196 because it's a perfect square. We still have a 3 in the bottom. Doesn't matter. You have a calculator. Equals h squared. So then you get to h from this, and instead of plugging in h, you should plug in h squared to find out what r is. H squared is right there, right? So plug it in there and take the square root of, like, after you plug in 196 over 3 for h squared right there, and then divide that by 4, take it away from 49, blah, blah, blah. Take this square root to get r. From here, you can get h. And so then using those two, you'll be able to find, it says find the dimension. So, in the end, answer the question, because the last thing I was looking at is like, well, is it telling us find the maximum volume? In which case, you'd have to plug them into this formula, or like a better version of it with just h is like, once you have h is this place, if it was asking for volume. But it's asking for dimension, so you're good. All right, these two, obviously, like, the examples are ordered, so these two are supposed to be like the most challenging examples of the bunch. Like problem 4, I'm pretty sure your teacher is not going to give a problem like that. It's not because it's hard. It's actually a pretty, example 4, it's actually a pretty cool, fun problem, but I just didn't think it was too relevant to like what you're seeking to accomplish. That's why we didn't do it. So I think this is good, unless you have other questions that you came up with. I think this is good.
No.
Okay, go ahead. Sorry, say that again?
I said I didn't have any more questions.
Okay, great. All right. Have a wonderful day. Thank you for being amazing as always. And good luck, but you don't need it. Work focused hard and you'll do well, okay?
Thank you.
You're very welcome. Have a good day. Uh-huh.